to give today's JQI seminar. I've known Antoine now for more than 20 years, which is kind of shocking for me to think about. We were both postdocs in the laser cooling and trapping group ages ago. And when Antoine was there, he did some fantastic experiments with BECs in optical lattices. And they wrote this paper, which was affectionately called the stupid lattice tricks with a BEC. And for the younger one of you, you don't know this David Letterman show that had stupid pet tricks where you would get pets and they would do. And they basically put BECs through their faces and did all kinds of stuff. And after he left the laser cooling and trapping group, he went to Institut and worked with Philippe Granger and doing single atom trapping. And he's been doing that ever since, but with ever more sophisticated techniques and much more interesting physics than you would imagine you could do when you first start trapping individual atoms. And if you think of what you think of when you think of a pioneer in a certain field, it's not just somebody who does something first, it's somebody who goes into a direction that other people aren't going. And Philippe and Antoine and later on Mark Safman really went into this single atom trapping work. And I remember at the time people told Antoine that Rydberg stuff was not going to work, in no uncertain terms. And they pushed forward and went into that direction anyway, and really pioneered that area. And it's really delightful to see how far it's come. And the fact that once you get out into a certain area, other people see the gold that's in the ground and, start coming in waves. And the field is really rich now, and there's a lot of people working in it and doing some fantastic stuff. And I look forward to your talk.
Thank you very much, Trey. So good morning, afternoon, whatever, morning, everyone. So it's all right? People can hear me? Or? Yeah. Okay, so just for the Zoom thing. So it's a real pleasure for me to be here after 4 years of unusual times, let's say, to be back to a place which is very dear to my heart, and also because there are so many friends that I've known for years, as you said, decades actually even. So thanks a lot for the very kind introduction. I better not screw up the talk now. So what I would like to discuss are results that we had over the last few years, essentially the last year, around magnetism and spin squeezing using arrays of Rydberg atoms. So this work is done at the Institut Optique. So technically speaking, and despite the Eiffel Tower, the Institut Optique is not in Paris. It's actually 20 kilometers south of Paris on the campus of Université Paris-Saclay, which is the largest cluster of labs actually in France. This has been created 5 years ago, something like that. All right. So this picture here that I was discussing with Bill is supposed to illustrate me assembling atom by atom some kind of matter, and the matter here is a diamond. So it brings two wrong ideas. The first is that I do something, which is not true. And secondly, that we are very rich because there is a diamond. And that's okay. Could be worse, but it's not exactly the case. So the people who actually do the work, so this is our group actually at the end of last year. So we had a few people that left and others have joined, but this gives you the size of the group. So we have two permanent staff members, so Thierry here and junior one, Igor. So both are CNRS staff member, if you wish, it's a bit the equivalent of NIST, so federal employee. And so we have a team of postdoc and a PhD student. And the one who are really the heroes for what I'm going to discuss today are actually Guillaume, Gabriel, and Cheng, who is postdoc. Supervised by Daniel, who used to be a postdoc in our group, who is now back in Spain, and Thierry. And we receive some theory support from Adrien Leclerc. Very importantly, for what I'm going to discuss, everything is done in collaboration with theorists and theorists of the condensed matter physics. So there is Norm Yao in Harvard, Andreas Leuschli in Lausanne and Thomas Orosilde in Lyon, and together with their team, of course. All right, so there, the advertisement, as everyone else on the planet, we're looking for PhD and postdocs. Kind of tough to find people those days, as you are well aware of, I'm sure. And I'm not going to bring you any deep introduction about what we do, about quantum simulation, about all these things, because I'm kind of assuming that you know that. But so essentially what we do, we have 3 projects, and with those 3 projects, we explore problems in many-body physics that you, as we move along, you will see what they are, using those quantum matter that you assemble either atom by atom, or you use some kind of bulk gases. So we have 3 projects in the group. The one I'm going to discuss is the one related to Rydberg atoms. And typically there we make the atom interact when they are separated by distances of few micrometers, so very far away and very far apart. You will see how we do that. But we also have another project where we use a very dense atomic cloud. So those are laser-cooled atoms as well. The typical interparticle distance is much smaller than the wavelength of an optical transition. And so there you shine light. The light induces dipoles, and you look at what happens if those dipoles interact strongly when they are separated by less than the wavelength of light. So you can see that as quantum optics, or you can see that as well as driven dissipative system that you try to study. And Igor in our group has started a project which is kind of a combination of those 2 physics. So essentially exploring the physics of this driven dissipative system using the tools that we have developed for the Rydberg. So he's building an array of dysprosium atoms. We can discuss later if you wish what this is all about. And since essentially 2 weeks ago, so he managed to have some small arrays of dysprosium atoms in his machine. All right, so what the platform I'm going to discuss is about is arrays of atoms. So I will sweep a lot of details under the rug, but essentially we start from this kind of picture. So this picture is a fluorescence picture of individual atoms. So essentially each of the dots you see here corresponds to one and only one atom, which is trapped in one of these microscopic traps, which we call an optical tweezer. So I don't tell you exactly how we'll produce that. This is the starting point of what we're going to discuss for the physics. So that's, as Trey very kindly reminded, was actually pioneered by Philippe de Grangier in the early 2000s at the Institut d'Optique. And so now these kind of machines are actually very popular in many labs, and you can assemble atoms to a few hundreds typically in 1 dimension, 2 dimension. You can even assemble totally random structures like this one. So that's something we've done during COVID when all the museums were closed. So you have to build your own museum in a sense. You can, more interestingly, produce figures like this is supposed to be a defect in a crystalline structure. So in order to explore many-body physics problem in such structure. And you can also assemble it in 3D. This is this iconic Eiffel Tower. So far, we haven't done any physics with that. It's just more to show off. Actually, there are some experimental difficulties in trying to use that to explore many-body physics, but this is clearly something on the agenda. The largest number of atoms we've been able to assemble in this way was about 340. And this is based on a new setup we had developed for a short time before we stopped the project. But essentially, we wanted to demonstrate that by improving greatly the vacuum, essentially going cryogenic, then you don't have background collision any longer. And therefore, you can extend the lifetime of your array, because the big issue is that if you have an array of n atoms, the lifetime of the array is divided by n, obviously. So it's kind of a limitation if you want to scale it. So that's something we have tried, and quite successfully, because we could keep the atoms for 6,000 seconds, so essentially 2 hours. So a time which is long enough to assemble large arrays. All right, so these are the starting point, atoms separated by a few micrometers. So of course, at such a distance, they do not tunnel, they do not interact. So you need a tool to make them interact. And this tool is to promote them to highly excited state, which are called the Rydberg state, as you all know. So typically, if you want to have a pictorial image of this, it's an atom where the electron spirals far from the nucleus. And it has 2 consequences. This large principal quantum number is very long lifetime. Well, long, okay, let's not exaggerate. It's typically a few hundred microseconds, but it's 10 to the 4 times longer than if we were using low-lying transitions, right? So it's long on an atomic timescales, and more importantly, even the fact that they develop large transition dipole matrix element. And the consequence of this, of course, is that they develop large dipole-dipole interaction. So that was those ideas suggested in the early 2000s by Misha Lukin and Peter Zoller and many others. Actually, there is one very important contributor to this in this room. The first experimentalists who took these ideas seriously, as Troy pointed out, is Mark Safman, University of Wisconsin, and we joined a few months later. So the consequence of this large dipole, as I say, the large dipole-dipole interaction. So if you want to have some kind of orders of magnitude in mind, typically if you take two Rydberg atoms separated by about 10 micrometers, the strength of the interaction expressed in megahertz is 1 to 10, typically. And so now you see why these 100 microseconds, despite the fact it's not super long, it's long enough to do something, because if you look at dynamics which are driven by the interaction, actually the time scale has sub-microseconds. So to a certain extent, you can kind of ignore, I mean, of course, if we push very far the fidelities, you have to bump into this, but at least for proof of principle experiment, you can ignore the finite lifetime of the system. All right, so sure.
Away from that slide. The picture of the fluorescence picture. It looks like there's some kind of a global distortion.
Yeah, there is.
Doesn't correspond to any simple aberration.
It's simple aberration. I mean, typically the lenses we use have a field of view which is supposed to be about 30 micrometers. So 30 micrometers, it would correspond to kind of a circle which is here. So you do see that indeed we are pushing way beyond the field of view. It's a problem. It's not a very detrimental problem. So you see that actually typically it looks like you've got coma aberrations when you go on the side. And this is exactly what you have, both for the imaging and for the trapping as well. But when we do the experiments, the atoms are all in free flight. So in a sense, the aberration for the trapping do not matter any longer.
Yeah, but I guess what was bothering me was that, for example, I'm seeing a strong aberration on the lower left, and not so much on the lower right.
Well, you know, you have to, because it's not aligned at the center of the field of view, I'm afraid. This is as simple as that. Now, this is a bit tricky, I mean, the alignment of all these things. So we try usually indeed to have a figure which is as symmetrical as possible in order to indeed make sure that we are really at the center of the field of view. It may not be the case for this particular one. All right. So Rydberg atoms have two ways to interact. It's not only Rydberg atom, but any atom. So essentially, the first one is the typical van der Waals interaction. If you place two atoms in the same Rydberg state, they will have an interaction energy which is diagonal. I will say a bit more about that in a second, which essentially shift this energy level by C6 over R6. Okay, and the C6 coefficient for Rydberg atoms scales very violently with n, and that's the reason why it's useful to use Rydberg atoms. The second type of interaction, which is mainly the one I'm going to use here, is the resonant dipole-dipole interaction that I'm going to explain a bit more in a minute, but essentially that scales like 1 over R cubed instead of 1 over R6. So the van der Waals is essentially what everyone uses in the community, apart from us at the moment, but we probably more soon. So this was the initial interaction that was suggested in the paper of introducing this idea of Rydberg blockade. The thing is that from the point of view of many body physics and spin models, it implements a quantumizing model. Okay, so essentially you've got a diagonal contribution, which is the Ni and J. You've got two atoms. Ni is if the two of them are equal to 1, you have a shift. If only one is 1, then you do not have any shift. So you need the two atoms to be in the same Rydberg state so that they interact. And you've got the driving field, which is a laser field driving this. And the two parts of the Hamiltonians do not commute. So that's the thing that makes it quantum. And so we studied that quite a lot. I mean, and so did actually Misha Lukin in about the same time. So we tried to prepare antiferromagnetic state in those structure on square arrays and triangle arrays. And I'm not going to say more about that. So essentially, this is a traditional interaction which is used in this business. But so the one we're going to look at is the other kind of interaction, which so far people have not used too much. And so it means that everything we're going to do will be in the Rydberg manifold. So it has some kind of obvious experimental drawbacks, but let's ignore them. So we start by preparing our atoms in the tweezer in a well-defined ground state, and we do the laser excitation to, let's say, a state which would be 60 S1F, but it doesn't really matter. It's the starting point. So essentially, I'm going to ignore all the low-lying state and only work on this two-level system, having picked up some relevant Zeeman structure, and all the physics of the two-level system will be done on this transition. As we said, this transition has a strong dipole matrix element, and as a consequence, it's very easy to drive a Rabi microwave transition. So this is an example of a Rabi oscillation on a single atom, which is driven on this transition, which is around 17 gigahertz for the frequency. From the point of view of the interaction, what the dipole-dipole interaction does is that it allows the following process to occur. So essentially, if you place one atom in spin down, the other one in spin up, and vice versa for the second, the other one is spin up, what the interaction is going to do is to flip the state of the two atoms. Okay, so there is no van der Waals here. It's just what is called a resonant interaction because those two states have the same energy. The two atom states have the same energy. So up, down, and down up have the same energy. So that's the resonant process. So that's something we measured actually a while ago, already in 2015. So essentially you take two atoms separated by 30 micrometers. So that's a huge distance actually on the length scale of an atom. And yet you can see indeed that they exchange their state alternatively up and down as a function of time. So what this does is that it implements what is called the XY model. So this is a flip-flop interaction. So this is sigma plus sigma minus plus complex Hermitian conjugate, sigma plus being the raising operator and sigma minus the lowering operator. The strength of the interaction here is directly given by 1 over r cube. So this is this 3 over r cube type of interaction. And you can rewrite, this Hamiltonian in the following way. It's going to be useful for what I'm going to discuss in a minute, like sigma x plus sigma y. So this is just rewriting the Pauli matrices in a slightly different way. Okay, so this is something we've used as well a while ago to implement some kind of transport experiment using what is called an SSH model. If you don't know what it is, you're not going to learn that, but essentially that's something that was our first experiment towards the many-body regime using this type of interaction. That's not what we're going to discuss today. So those are the three things I would like to discuss.
Go back to the previous
Sure.
one. So there's this beautiful oscillation. And it's decaying ever so slightly. What is controlling that?
Yeah, so there are two things. First, it's decaying, and second, the contrast is not optimal. It's not one. So the fact that it's not optimal, that was the first one of the first curves that we had, is just because we did not initialize the two states properly in the Rydberg manifold. So essentially, all what you have here, the extra, missing amplitude, comes from atoms that were left in the ground state during the Rydberg experiment. And now it would be much better. The slight decay, it comes from essentially the fact that the atoms are in free flight when we do the experiment, and therefore they slightly move away from each other or whatever, and therefore the coupling changes as a function of time, which once again is an obvious drawback of this. You can trap the Rydberg, we've demonstrated that, but on large scale it's a bit demanding. All right, so this is what I would like to discuss. And of course, I know this audience. I'm pretty sure I will not be able to reach the end of the talk. There will be questions. And so, but okay, it doesn't matter. I mean, I'll try to cover what is relevant without bothering you too much. So we will try to go in three steps. So essentially, we'll try to build a ground state of this Hamiltonian, this XY Hamiltonian, and explore both the antiferromagnetic configuration and the ferromagnetic configuration. Second thing, and this will be work that is ongoing work and not published, so things that I will say may not be totally right or may change as time goes on, but we'll try to measure the dispersion relation of this thing, so the excitation, and you will see why it's interesting. And finally, if I have time, I will discuss a bit how you can zoom out from there and take another point of view and describe an out of equilibrium situation as the buildup of spin squeezing in the system, which may be useful for interferometry. Okay, so let's start with the dipolar XY magnet. And so once again, that was something that started as a collaboration with Norm Yao and Mike Zeletel when they were still both of them in Berkeley. So the Zoom were a bit intense on Friday evening with 9-hour times difference, but okay. And the lead PhD student is Marcus Bean. We have just done an awesome job at doing the simulation for this experiment. And we also had Andreas Löschli and his student Michael Schuler contributed to this experiment. So what's the thing? So essentially, if you start by taking the usualizing model, which is the first model, spin model that we encounter when we learn statistical mechanics. So this is a model which you can write like an XX, sigma X, sigma X. And so let's take, for example, an antiferromagnetic configuration. We know that at half filling, you will have a staggered configuration of spin pointing along X or minus X. So those are all classical configurations that have a name. They are called a nail configuration. And this is essentially the configuration that people have studied, either us or Misha or a few others now, on square and on triangle. So the ground state of this, in a sense, is not super exciting in the sense that it's completely classical. The way you reach this state may be quantum if you implement the drive, but here, let's just take at the interaction part. Those are classical configuration. Now, if we look at the XY model, things are immediately a bit more interesting from the quantum point of view, because you've got two competing orders. You've got the XX, which have a tendency to align the system along X, either ferromagnetic or antiferromagnetic, depending on the coupling, and the YY, which will have a tendency to impose an ordering along the y-axis, and the two do not commute. So you've got two competitions. So at the end of the day, if you want to have an idea of what the ground state of such an Hamiltonian is, so you cannot write analytically explicitly, but a good ansatz wave function would be to assume that it corresponds to a ferromagnet, let's say if you're in the ferromagnetic case, and you allow any superposition with any angle. Okay, so that's a kind of an idea that you can get for this. So it all lies in the XY plane, and it's a superposition of classical configuration that you rotate along this phi angle. The true ground state a bit more complicated, and in a sense a bit more interesting, because it's dressed, this ground state, those ansatz, by the appearance of pair fluctuation. So essentially you can have two spin-ups suddenly that emerge from that. Okay, so of course, this has been studied in many systems. You have a traditional system where you can look at that, this kind of system, so metal organic compound. So essentially, you can have a square array of reasonably complicated structure, but essentially the copper ions kind of carry a spin 1/2 system and implements more or less the spin 1/2 things. And people have looked using neutron scattering, what is the excitation properties of this thing. There is also a platform which I find kind of nice, where people could implement titanium ionium on an NGO surface and kind of build very small square arrays of this. So that's a way to look at this XY model. And of course, there is a lot of work that has been done in the context of ultra-cold atoms in optical lattices, where that was kind of an experiment by Marcus Greiner in Harvard, where he could see the antiferromagnetic ordering of the spin in this in a 2D structure. So the thing is that more or less all these experiments implement not exactly the XY model, but the more general, or not more general, I don't know, but the Heisenberg model, which is more the SI.SJ thing. But very importantly, it does that with short range interaction. And you will see that using long range interaction significantly modifies the picture. So if you have short range interaction, it's actually kind of almost textbook material that the excitation spectrum has different behavior depending whether you are ferromagnetic or antiferromagnetic. So if you are ferromagnetic, you are supposed to have a K-square dispersion relation at the beginning. While in the case of the antiferromagnetic case, you have a K. So it's like a phononic, if you wish, dispersion relation, which is associated with what people call a Goldstone mode. Although when I say that, I don't know what I'm talking about. But okay, so this is what those excitations are. Here, this is not what we have. We have dipolar interactions, so 1/r cube, and this actually is very hard to find in real materials. It's really screened by more dominant interaction scales, but this is very relevant for artificial quantum matter, because polar molecules, magnetic atoms, if you take atom-like defects in solid, like in NV centers, for example, will be governed directly by these dipole-dipole interactions with 1/r cube. And the thing is that it immediately introduces an interesting aspect. If you assume that you have a negative coupling, so essentially an antiferromagnetic coupling, you see that you have the competition between two possibilities. So if you have the antiferromagnetic coupling, essentially the coupling tends to form anti-parallel bound along one axis. Okay, so if you do that, what you have is up, down, down, up. which is in competition with the antiferromagnetic ordering along the diagonal, which, okay, is weaker for sure, but still it exists. So what this does, this 1/r cube, is that it introduces a non-negligible frustration in the system. Okay, and this non-negligible frustration is strong enough that it should modify the dispersion relation. So it should modify not the antiferromagnetic dispersion relation, which is kind of fragile, but the ferromagnetic one should go from k squared to square root of k. And I will hope that I can show you our results where we measure this modification. From the point of view of the ground state itself, there are two cases to consider. If you are exactly at 0 temperature, both the ferromagnetic and antiferromagnetic case are supposed to feature what is called long-range order. So long-range order means that if you look at the correlation function between spins, so these XX correlators, when you separate the two spins at a large distance, it doesn't go down to 0, but instead it kind of plateaus, and this is what is called the long-range order. When t is not equal to 0, then the behavior is supposed to be different. You still, in a sense, the ferromagnetic phase is supposed to be robust enough up to a certain temperature. If the temperature is too high, you break everything, obviously, but you're supposed to keep the long-range order. Why, if you are the antiferromagnetic case, it's reasonably fragile and you break very easily this long-range order. So the frustration kind of destabilizes. Please.
Why is there frustration for the ferromagnetic phase where all the spins are aligned, the diagonal? Same arrangement.
Well, then you don't have the frustration in this case. Because in a sense, well, okay, my slide is probably poorly laid out. The frustration is really for the antiferromagnetic case. Okay, and as you can see, yeah, okay.
So is that mixed up then? Because it says the antiferromagnetic.
Yeah, and indeed, the antiferromagnet is not modified. This is the ferromagnet which is modified. That I propose we will discuss that in 5 minutes after another slide, which usually confuses people. And unfortunately, I'm not quite sure how to completely prevent people from being confused. But okay, let's try. So this is an important question, and you're asking. So the point is that this long-range order in 2D in any system has never been observed, actually, strictly speaking. So what I will try to show you that we have evidences that you can build that onto small systems. So now, how do we do that in the lab? So we start from the resource Hamiltonian, which is the interacting Hamiltonian. So 1/r cube XX plus YY. Here, the coupling is positive. So with minus J, you have a tendency to favor ferromagnetic coupling. And then you will add to that, and I will tell you in a minute how you do it in practice, but you will add a staggered field along Z. Okay, so, and the control parameter in our case is going to be this effective magnetic field along Z. And so now the procedure is the following. We want to prepare the ground state of either the ferromagnetic or the antiferromagnetic state. So what we do first is we start by preparing a classical Néel state, so an antiferromagnetic state, along the Z configuration. Okay, how do we do that? So we start with actually all the spins pointing down. So remember, pointing down essentially means they are in the ground state, but in the Rydberg manifold. This is not the true ground state of the atom. At some point, you just apply laser beam on every other atom. So you've got now two staggered configurations. So those laser beams are going to shift the energy level of all the atoms B there, leaving untouched the other one. And so each of the beams are addressing this kind of staggered configuration. And now you apply a microwave flip in order to flip half the atoms, so the one that do not see the addressing laser. Okay, and in this way, you've prepared this antiferromagnetic configuration along Z. And so now what we're going to do is we're going to adiabatically ramp down this staggered field. So now this delta I, once again, it's equal to delta on B and 0 on A. Okay. And so now if you do that, what you'll see is that you can access either the ferromagnetic or the antiferromagnetic phase. It's just that in one case, this is the true ground state of the system. In the other case, this is the most highly excited state. But at 0 temperature, in principle, it doesn't matter whether you deal with the highly excited state or the ground state. So the way to do that, I mean, let's, for example, start with delta, which is initially negative, and you can do that by choosing the wavelength of the laser. Then, by adiabatically sweeping down to 0, you prepare the state which turns out to be the antiferromagnetic configuration in this case. On the other hand, if you had started from delta positive to start with, ran down the detuning, you would have obtained the ferromagnetic case. So it means that on this single machine, you can, just by changing the sign of the detuning, access both phases and therefore do differential measurement between the ferromagnetic and antiferromagnetic case. Irrespective, and that's very important, of the sign of the coupling, which is a bit what the question you were asking. You have a ferromagnetic coupling, and yet you can prepare the antiferromagnetic phase with this. Okay, so let's try to do the experiment. So we initialize our nail state, and at some point we will start ramping down the deltas, and then we will read out in the Z basis what is the magnetization of the system. So essentially, we will measure the magnetization, so the number of spin up and the number of spin down, on the two sublattices. And so one is prepared initially up, the other one is down. But as we are along the Z basis, but as we run down, we kind of melt the magnet into something which is in the XY plane now. So I should not have any magnetization along Z any longer. And this is indeed what you observe, starting from the antiferromagnetic nail configuration. You melt that down, and indeed it goes down close to zero. So there is a slight asymmetry, which is just experimental imperfection, which we can discuss, but essentially it should be the same final value here. In the antiferromagnetic case, you do the same thing. It's just that the timescales are a bit different, and that reflects the fact that there is kind of a phase transition. It's not occurring at exactly the same time. The antiferromagnetic is much more fragile than the ferromagnet, and therefore the phase transition occurs actually later for much smaller values of delta. You want to cross-check, so this is the magnetization. So essentially your magnetization.
So on the ferromagnetic piece is absent here.
Exactly, because the way of preparing okay, so it's a bit subtle. It's just that because the time at which you reach this plateau is different, it means that in the antiferromagnetic case, the addressing light is applied for a longer time than in the second case. And that leads to a partial depumping of the atoms, which kind of break the symmetry up down. The atoms kind of go away from the two-level system. So that's what leads to the asymmetry. So that's the reason why I was mentioning it's an experimental imperfection, which comes from the fact that the addressing laser induces spontaneous emission. And because the ferro and the antiferro are not exposed to the light the same duration, it leads to an asymmetry. Okay, so I mean that we had model and it kind of works. And so so the second thing is that, of course, you want to check that in the XY plane, things occur the way they should, so that you have the correlation that you should have. So we're going to measure now, not in the Z basis, but in the X basis. So it means that before doing the readout, you apply a short microwave pulse to bring that back to the Z state, and you measure the growth of the correlation between nearest neighbor and next nearest neighbor. In the ferromagnetic case, you do observe that the correlation grow as they should, and at the same time. While in the antiferromagnetic case, you can see that they also grow, but with opposite sign, which is the signature of the antiferromagnetic ordering. You also see that actually at longer time, they start to kind of decay, and this is because exactly the point Bill raised initially, which is the atoms starting to move. Actually, we start to have some breakdown of the order. All right, so there is kind of an interesting question, which is what kind of state do we prepare? The correlation measurement that I showed you actually is unable to distinguish between the preparation of a classical ferromagnet or antiferromagnetic in the XY plane or this superposition that was mentioning, which is supposed to be the true ground state of the XY Hamiltonian. So the point is that you can distinguish that by just looking at the variance of the magnetization along Z, because if you add the ferromagnet and you prepare that, you should have a true magnetization. It's an eigenstate of the system, so the magnetization, the variance should be zero along Z. While if you add a classical state, each pointing in any particular direction, it can be random at each realization, you should have this kind of tensor product here of up and down, and it should build a binomial distribution along the Z distribution. So just by looking at the variance of the distribution along Z, you can separate from a classical state from this quantum superposition here. So we've done the measurement, and okay, so it's not perfect, obviously, but we see that if we were supposed to have a variance, which should be this delta function, actually we find that indeed in the ferromagnetic case, which is for this case, the variance is slightly lower than it should be. So essentially, if I plot the variance as a function of time, we do see that indeed the classical state, which should correspond to this, should be at this value, and we have something which is reduced. So this is not the proof that this is perfect, but this is the proof that at least it's not a purely classical state that you prepare in the X prime. Okay, so that's kind of an indication that indeed you at least have part of the superposition. All right, so the last thing that we can do, of course, is to build a correlation map now. So instead of just looking at the nearest neighbor or next nearest neighbor, you can build what is called the connected correlation function, which is this quantity, which is the correlation between spin along X at a given position and I, let's say, and the probability to find another one still in up or down in the other direction, sorry, at another position. And so in the ferromagnetic case, you find something which is all red. Red means that you always have a positive correlation function. If instead you had prepared the antiferromagnetic case, you got the usual staggered configuration, up, down, up, down, up, down, as it should. But you also see that it seems to decay kind of more rapidly, and this is a consequence of the destabilization induced by the frustration. Okay, so now let's grow the system size. All what I've shown you so far was done with a 42 atoms, so essentially 6 by 7 array. So now we could enlarge a bit the number of atoms up to 100. And we looked again at this correlation function. And we're going to kind of make it a 1D diagram, if you wish, by looking at the value of the correlation, but not as a function of distance now. So I have two indices, I and j. Now I just kind of average over all the spins that are at a given distance. And what we see is that there are indeed two different behaviors, depending whether you are ferromagnetic or antiferromagnetic. What you observe is that at long distance, in the case of the ferromagnetic, the correlation never go down to 0. And this is precisely what we hoped we would do, we would see. And this is backed by some calculation that actually the guys have done in Berkeley, where indeed you expect from DMRG calculation some kind of long-range tail, long-range order. I mean, you have to be very careful. The scales here are not the same as on this side. So quantitatively, we don't understand the value, but the phenomenology reproduced. So this is the evidence of the long-range order. So for those of you who wonder about Wigner, Mermin, Wagner, and all these things, I mean, whether it's relevant, I don't know, because the system is so small that it may not just be a problem. But essentially, you should not have long-range order in this situation. In the case of the antiferromagnet, this is exactly what I told you. So essentially, at T, at temperature which is non-zero, you should not have any long-range order. And this is what we have. So now you're going to ask me, okay, what's your thing about temperature? I mean, aren't you at 0 temperature? The thing is that the initial state preparation is not perfect. Okay, and that's a key point here, because it means that you have an initial entropy or initial energy, if you wish, in the system, and therefore some kind of equivalent temperature. Doesn't mean that the initial state is thermal, but it means that it's an imperfect state. And so this is those imperfections that destabilize the order and that kind of mimic the effect of a temperature in a way which I'm doing the thermometry and the system is actually fairly hard, but okay. But okay, the thing which is interesting now is to see that this 1/r³ interaction actually modifies the behavior of the magnet. If we had nearest neighbor interaction, both ferromagnet and antiferromagnet should be completely symmetric and exhibit exactly the same behavior. Okay, so how am I doing with time? Not too good. Okay, so let me now show you the consequence on the dispersion relation. So we're going to excite the system and see indeed that the dispersion relation is different again for the ferromagnetic and antiferromagnetic case. So once again, this is work in progress. This is not published. I may say things that actually proved wrong and will be different in the final paper. So it's not too important. But so this is again a collaboration between Norm Miao and now Tommaso Rosilde, working in Lyon in France. All right. So just, and this is really a spin wave theory for dummies like me, just to try to sketch very rapidly how you write and you can understand the excitations above the ground state. So the thing is always done the same way. You apply what is called linear spin wave theory. So you start from the spin Hamiltonian that you're having, and you replace the spin operator by particle operators. Okay, it's a bit more complicated than what I'm outlining here because they are bipartite lattices, but it's not important. The important thing is that you go from spin to particle. So essentially, a sigma plus operator is the equivalent of a B dagger operator, which creates a particle somewhere, if now you see a spin excitation as a particle. So then you do usual thing, which is you introduce the Fourier transform of those operators, and you also introduce the Fourier transform of the potential. But here, the situation is different whether you have ferromagnetic or antiferromagnetic coupling. So essentially, for the ferromagnetic case, you should have a staggered configuration of e to the I QR divided by the r to the cube in our case, while for the antiferromagnetic, it's a staggered configuration. So the two cases, the potential is not the same. So now you do the usual thing, Bogoliubov transformation to diagonalize the thing whatsoever. And at the end of the day, you arrive to an Hamiltonian, which has this kind of form. That's the form of some kind of ground state. And it turns out that in the case of long-range interaction, you have to be very careful how you handle the Q equals 0 spin wave. So I'm not going to discuss that too much, but people have done that in those two papers. But the thing which is relevant to us is this part here, which is the typical thing you always find when you deal with quasi-particles, is the fact that this is a bunch of independent particles with an energy which is given by the dispersion relation. And this dispersion relation is directly connected to the Fourier transform of the potential, so this GQ, for Q non equal to 0 or Q equals 0. Okay, so at the end of the day, this is the important result. And the second important result is the fact that, so those excitations, sorry, are called the spin waves, is that you can calculate the structure factor. So the thing that we have measured, that I showed you, these two axes I and J, Cij. If you take the Fourier transform and apply also the spin wave theory, you find out what is called the structure factor. It's not exactly the structure factor in condensed matter physics, which requires two time correlation. Here, everything is done at the same time. This is the Fourier transform correlation along Z. And the thing which is interesting is that this temporal structure factor, which now we can easily measure because we have directly the correlation at a given time, is directly related to actually the dispersion relation. So you find that there is a constant term, which is the ratio of GQ over G0, so essentially the same thing, and then it should oscillate at a frequency which is directly the dispersion relation. So it gives us the procedure to apply in order to measure the dispersion relation. And the important point, once again, is that it's going to be different for ferromagnetic and antiferromagnetic case because of the staggering that you have here. So this is, again, this square root of k or k square difference that you have for the ferromagnetic case. All right, so let's do the experiment. We start from the atoms initially in the ferromagnetic case along Z. We apply a pi over 2, so the system is out of equilibrium, and we just measure as a function of time the correlation map. So, I mean, this diagram is actually fairly difficult for me to completely understand. But essentially, this is, again, the correlation function along Z this time. So there is no rotation or whatever that you do, apart from the initial state preparation. And once again, because I will have distance and time, I need to wrap my 2D thing into a 1D distance. So that's the square root of this I square plus J square. So what you see that very rapidly at the beginning, you start building anti-correlations in the system. And that you also have some kind of structure, which I have to admit we don't fully understand. So then you have some kind of plumes in a sense of positive correlation that occurs. Okay, the thing has a structure. And so what you can do is to Fourier transform this and obtain this time-dependent Fourier structure factor. And you observe that essentially, if you plot it, the time is on this axis, and Q, which has two indices again, so QH and QY, which I wrap into a single Q, you observe some kind of oscillation before the system kind of reach some equilibrium. And so the oscillations are kind of obvious at the beginning, less obvious at the end, but it's possible to do a fit which is reasonable. Sure.
Yeah. So this linear response theory is S of Q and omega dynamical structure factor.
So sorry, I don't hear.
Understand. I can speak loud. So I usually understand that I have a ground state, and then I excite the system, and then look at the linear response.
Exactly.
Right? Here you're quenching the system.
Yes.
So you're completely changing the answer.
Yes. So that's a very good point. So the traditional approach in condensed matter physics to measure the dispersion relation, you prepare the ground state and you flip one spin and you look how it propagates. Or you just probe by neutron scattering or this kind of thing. exactly, or Bragg scattering. This is not what we do, because I mean, the reason why it's not what we do is because this is a difficult experiment for this machine. The reason for that, it takes a lot of time to prepare the ground state, and we start to fight the decoherence associated to the motion before we can do any measurement over the ground state. So that's a big problem. So instead, we do this quench. The reason why it seems to work, and this is still something we're investigating, is that when you quench, you are not actually not so far from the true ground state of the system, in the sense that if you measure the density of spin wave you put in the system above the ground state, it still remains small. It's true for the ferromagnet, it's not true for the antiferromagnet. The antiferromagnet develops a huge amount of spin wave, and therefore we expect that the linear spin wave theory would be violated for the antiferromagnet. But as a matter of fact, your point is a very important one, because you see that all these oscillations kind of decay. Why do they decay? At zeroth order, it's a violation of the linear response theory, where the quasi-particle starts to interact and leads to damping, a dephasing of the quasi-particle.
And it was not possible to do perturbation. If you have your Hamiltonian,
well,
add some
no, I'm sorry. It's just that we haven't tried. It could have been possible, but the procedure to prepare the ground state is a bit plagued, essentially because the entropy of the initial state is much worse than it is in a quench thing. And so that's the reason why we felt that the ground state would prepare is actually not so good, and that it would be more difficult to see the excitations. But maybe we're wrong. We haven't tried. It's just a feeling. So the second case, obviously, is to repeat the same experiment with the antiferromagnetic case. So we have kind of the same procedure. We plot the correlation function, and then we try to take the Fourier transform. So you see that the oscillations are actually much slower, and they're actually more damped, and it's probably a violation of linear spin wave theory in this case. And so now you can wrap all this onto a graph. So this is what we have. So this is the frequency that we extract from the oscillations. And you're going to tell me, well, I mean, this is very bad. You've got a lot of noise. But actually, this is not noise. This is the fact that you are plotting your omega of Q as a function of square root of Qx squared plus Qy squared. Think about your single, if you have a 2D array, and you plot just the single particle band structure. It's cosine Qxa plus cosine Qya. So sorry, you don't see anything because it's behind. Okay, so this is the usual thing you have in the tight bending regime. And now you want to plot this thing as a function of square root of Qx squared plus Qy squared. And so it will start. You will create this kind of fun type of structure. So this is exactly what we see here. So the dispersion is just due to the mode of representation of the curve. Okay, you can do it in 2D, but as usual, it's more hard. It's harder to compare to theory. And as a matter of fact, so you do the same thing for the antiferromagnet, and clearly you see that there is a difference. As a guide to the eye, and this is not more than a guide to the eye, this is certainly not a fit, okay, you see that indeed it has a different behavior. Interestingly, if now you do a real theory on this, which is called time variational Monte Carlo, so it's not us who do that, it's Tommaso Rosilde, you actually see that the agreement with the data is reasonably good, including in the noise. Okay, the so-called noise, which is not a noise, this is just a way of representation of the system. Okay, so the second thing, you of course want to validate a bit this and make sure that what you're not fooling completely yourself. I remind you that this and you can you can see that from the previous slide. There is something also occurring at the time, at the final value at which the temporal function actually damps out. And so if you look at this, it turned out that, as I showed you from the slide on spin wave, actually you have an oscillatory term at the frequency of the dispersion relation, but you also have a constant and an amplitude. And the constant and amplitude are also related to these G0 and GQ, and then therefore are related to the dispersion relation. And if you plot this constant as a function of Q, so in again a mapping which for me is always complicated to understand, but this is a journey in the Brillouin zone. So you start from Qx equals 0, Qy equals 0, you go to pi, you go down there, and you wrap that down. So, and what you see is that indeed you have some kind of symmetrical behavior for the ferromagnet that you don't have for the antiferromagnet, for a reason that I admit I don't really understand. And if you extract from this way of representing the dispersion relation, using this formula, so essentially the offset is directly related to omega of q, you do find again a pretty good agreement. So this is kind of, again, a second nearly independent proof that you can extract the dispersion relation with this. Okay, so that's all I wanted to show here. And so how much time do I have? Shall I stop? Because I can squeeze the...
Go ahead.
So what?
Continue.
Yeah, but 10 minutes, 5 minutes?
Oh, but you've got like 6 minutes.
6 minutes. All right, so...
But it's a squeeze presentation.
It's a squeeze presentation. No, let me, so I'm not going to show you everything. But so essentially the idea of this last part is to step a bit back and say, well, let's try to understand now the dynamics under our XY model following a quench in a slightly different way. So we prepare initially the ferromagnetic case, okay, as we did before. And then we let the system evolve, but we will try to interpret what we observe in terms of a collective spin behavior. Okay, so you introduce this collective spin observable, so in this generalized Bloch sphere. And so what you find is that exactly what we found before, as a function of time, starting from a given magnetization along the y-axis, for example, the thing will damp down to 0. Okay. Now, the question that we're asking is that, is it just, okay, we know we create spin wave in this system, but can you say something interesting in terms of the quantum correlations between the spin themselves? So we are going to use a slightly different language, which is the spin squeezing language. And so just as a kind of short step back here, so essentially usually people describe spin squeezing in what is called the one-axis twisting model. So you start from this coherent spin state, which therefore has some kind of intrinsic noise along the two components z and x. So this is a projection in the plane perpendicular to the average. And the one-axis twisting model is a model where essentially you've got an Hamiltonian, which is the square of the total spin. So it's a nonlinear Hamiltonian. And this leads to the appearance of squeezing in the sense that you have this ellipse, which as a function of time gets squeezed with an axis, which now is twisted. And so people have defined a criteria that this leads to metrological gain in a Ramsey interferometer if you are using your spin up and down as a way to do interferometry. So the parameter was introduced by Dave Winan, actually, quite some time ago now, nearly 30 years. And this is the ratio of the minimal variance, so the one in the minimal axis, divided by the total spin length. Total spin length in our case is very important because it's going to shrink as a function of time. So you should not remember, it's not only saying that the variance is smaller than 1. You also need to have this chi-square parameter. And so the relation between this criteria and the improvement in the metrological gain is that if you were using independent spins or correlated spin, you would have a gain which is directly the square of this thing. So if this is smaller than 1, it means that the ultimate variance you have on your measurement is going to, of whatever angle, is going to be smaller by this chi-square. So now the problem is that we have an Hamiltonian which kind of looks like this. Especially, we initialize everything along y. So it means that essentially there is nothing, so to speak, along x. So it has a bit the same structure of this kind of ZZ coefficient that you would have for a GZ square, just along the y case. The problem is that here it's an all-to-all connectivity. So all the spins are connected to all the other ones. In our case, this is not the case, obviously, because you've got this decaying interaction. But so the question is 1 over r cubed long range enough to be able to generate squeezing? And so the prediction that is actually not so old, from the like 2 or 3 years, is that yes, it should. And people are looking at the class of entanglement of Hamiltonian, that could lead to this. And there is a conjecture that Norman Yao put on the archive a while ago, which, early this year. We said that if you have an Hamiltonian which features at t non-equal to 0 a long-range order, it's enough to get squeezing. So, I mean, these kind of sentences, for me, I will have to concentrate to understand what they mean. But and it just precisely what we have observed in the first part of the talk. We are at t non-equal to 0. We have observed long-range order in the ferromagnetic case. So, in principle, we should have squeezing. And this squeezing should be scalable. What this means is that the squeezing parameter should keep decreasing as a function, as you increase the number of atoms. All right. So, I will, so this is essentially the stake of what we want to do, and I will probably directly show you the result. you have to believe me in how we measure that. This is always the same thing. You kind of measure the magnetization, the variance, and you extract from that the squeezing parameter. So we've done this measurement for different number of atoms, okay, increasing from essentially 2 by 2 up to 10 by 10. We looked at the time the squeezing appeared, and we also look at the average magnetization as a function of time. And from that, you can extract this famous squeezing parameter at the best time. And indeed, you do see that the squeezing parameter, starting from 1, decreases when we increase the number of atoms by an amount which is about minus 3.5 dB. You can apply if you wish, because we kind of understand the type of error we have. If we were correcting from detection error, we actually could claim a minus 5 dB, but it's not too important. Essentially, it's the proof that indeed this the existence of this long-range order seems to be connected to the possibility to have scalable squeezing in the system. And just on a side note, I mean, what do we bring? I mean, this is a paper from like a few years ago summarizing all kind of possible way to generate squeezing in systems. So essentially what you have is the number of particles that people have used. So, and here, this is the metrological gain. So essentially the same chi-square as the one I showed you. And you've got different ways to do that. You can generate what are called GHD state. You can do that BEC in optical cavities. You can do that with all kind of different systems, and people have obtained a level of squeezing that are actually extremely high. So where are we here? We are there. We are kind of neither bad nor good. We're just kind of filling a gap in this landscape. So whether it's useful or not, I don't know. I should point out that actually at the same time, so many people are looking at this because there were 3 other experiments that kind of tried with complementary methods and complementary type of interaction to explore also the existence of these scalable squeezing in those systems. All right, so I'm essentially done. So I hope I convince you that also looking at this other type of interaction, the resonant dipole-dipole interaction with respect to the van der Waals that usually people study, is also interesting with Rydberg. So there are some experimental challenges which are different from using the van der Waals, but still you can observe nice physics. We've actually gone beyond that by being able to enlarge the class of Hamiltonian. Using an enlarged structure, you can actually engineer a spin orbit coupling, all based on this XY Hamiltonian. So it's just a flash, no explanation. So the thing, and that I just would like to finish with, is the fact that something which is a bit new to the landscape of this quantum simulation and quantum engineering business is the existence now of startups company, and there are actually 3 of them in the US exploring this Rydberg platform. So there is the oldest, I think, is the atom computing. There is a Quanta and Quera in Harvard. And so at the Institut d'Optique, we also have started one, which is now totally out of control, at least from me. So they are on their own, living their own way. The point is that there are actually 2 motivations to do that. The first motivation is trying to do better in terms of engineering than what we can do in a lab. I mean, especially in France, the PhDs are only 3 years, so it's very difficult to do challenging engineering development because the students don't have enough time to take advantage of that and have a physics paper out of that. So in a sense, what we hope is that the company can take the messy things we have in a lab in a shiny box, which does everything better, more stable, blah, blah. Okay, we can discuss whether it's so easy to do, but okay. And they're actually already kind of looking at this and also providing some open codes to simulate those systems and so on. I mean, so this is just the example for this company, but all companies have the same model. The thing also is to try to see whether those machines are useful for application. So be careful, I'm not saying quantum advantage, so I don't want to hear about that. I'm just saying it's kind of a new type of solution to explore problems. So let's try to push that as much as we can. And so they have already started. So essentially on small size system, and this is only proof of principle experiment, try to see whether you can, in a way or another, kind of optimize the charging of a fleet of electrical vehicles, which is a combinatorial problem. And already they saw that, yes, indeed, you can at least map the problem onto what those machines can do. And they've looked a bit more recently at other question, whether you can distinguish between 2 types of drugs in a kind of machine learning type of approach. So in a sense, it allows them to discuss with people outside the traditional fields of physics, and it's rich.
So does financial risk management on a neutral atom quantum computer mean
make sure you've got some AI stock.
No, it's kind of deciding whether the guys that you are lending the money to is actually solvable or not. So it's a credit history, I think, how it built. But I mean, I'm not going to bet a lot of money yet on this. So that once again, it's just a proof of principle demonstration. And from my point of view, and that's subject to debate, of course, the long-term goal of all these companies is build a quantum computer, okay? And no one has it, and no one has any idea how we're going to do it at the level of technology we have today. Nevertheless, for decades, we've just done it at the academic level with academic funding and academic mindset. At least this new type of ecosystem is a serious attempt to tackle the problem and say, well, let's put the money, let's put the resources, which of course you cannot do on government money and public money because this is a huge investment. And let's see whether this approach may lead to somewhere. And if it does not, it means that it's much harder than what we thought. But at least we have genuinely tried this thing. So that's a bit my take on this today, which may be different in a year or whatever. And so with that, thank you very much for your attention.
So there was this question there about like dispersion and frustration. You said that people always get confused. So I didn't quite understand what the confusion was. I guess the
No, well, yeah.
There was a square root of K, ferromagnetic.
No, the confusion. Some people
should be exactly like this because when you have ferromagnetism, there is actually constructive interference.
Right.
And it exactly modifies K to square root of K. And the antiferromagnetic, they interfere destructively, and it just stays. So it's exactly correct. So where there's frustration, it stays kind of normal. There's no frustration.
Well, I mean, for me, you have frustration each time you are trying to impose an order which is not compatible with the coupling that you have. And this is a bit what you're saying, right? I mean, so if you have this is not compatible with an antiferromagnetic order, but in the same way, if you have this is not compatible with the ferromagnetic order. So this is the way I see it. But the point where usually people get confused, and I'm not quite sure what to say actually to this is more, this is really tiny, below my capabilities to read out. Some people don't buy the argument, which is, I mean, this is interesting, and it will show the same excitation spectrum if I had the antiferromagnetic case. So in a sense, for me, the way I always understood these things is that it's a transformation in the Hamiltonian. Instead of having H, you've got minus H. But under this transformation, the dispersion relation of the system should be the same. But I had many questions about that, and I'm not quite sure how to answer this. Say that again.
The dispersion should be the same.
No, when I say, sorry, okay. I'm not saying that the two dispersion relations should be the same for the upper and the lower, but it's just, I think ferromagnetic coupling,
If you take the Hamiltonian and you just flip the sign, the fully excited state is the ground state of the negative Hamiltonian.
Exactly.
Yeah.
I don't know, someone like Zoranas Bilovic who understand this problem pretty well, is just completely stuck on this. It just doesn't believe that it will lead to the same excitation spectrum, which is to say that.
I asked the question earlier about the confusion, where that came from was not on this side of this argument. I think it's fine. It was, you gave an example with no frustration, and you said it was K and K squared, and then you add in frustration. So there seems like the new ingredient here. But that's only for the antiferromagnetic case.
Frustration actually doesn't exactly.
Right. So then, like, what's the new
ferromagnetic
ingredient on
enhancement.
the ferromagnetic case? It's not frustration. So there's a new ingredient, but
then is the long range
range.
interaction. This is the long range.
But I think that the confusion is.
Yeah. Okay. So sorry. It may be the way I presented it. Okay. Yeah. I should.
Antoine, you commented at the beginning about a dispersion experiment. So
Yep.
I presume that's not a Rydberg experiment. but
No, this one.
What are you trying to achieve with that class?
Well, the basic idea is that we would like to do light scattering experiment or like driven dissipative system. So essentially, you want a two-level system which is not only a coherent system, but which has intrinsic dissipation from the fact that it can decay. So now if you place many of them within lambda, you may have collective effect like superradiance, subradiance. And this is things we've looked a lot in a dense atomic cloud. I mean that in the dense atomic cloud, if you just take one atom in the center, it sees the field of all the others. So you have the collectivity, but because the phase of all these fields may interfere are totally random, and the effect is actually pretty small. So if now you structure the array, you may enhance or actually completely suppress the collective effect. So that's what we want to do. So why do we use dysprosium? The problem is that you want to have an ordered array of any possible geometries, if you wish, but you also want to be sub-lambda with respect to the transition you are using. So I mean, it seems incompatible from the diffraction theory, but if you use dysprosium, you've got two kinds of transition. You've got, and it's the same for strontium, all these atoms, you've got the blue transition and the red transition. And it turns out that so you can trap on the blue transition being sub-lambda with respect to the red transition. So this is the idea, and dysprosium is interesting because this is, from all the atoms that people have laser cooled and used, the one with the largest ratio blue to red. You see what I mean, red to blue. So that's the motivation. Yeah. And in passing, actually, there is a lot of interesting EMO physics to do because, for example, even finding the polarizabilities, I mean, what we measure experimentally is not compatible with what Maxence Lepers, for example, calculates. So there seems to be some kind of unknown on the position of some line. So,
One last question.
sorry, yeah.
Yeah, so I have a question about the non-range order. I think it's the next slide. So the theory that you compare with, that's presumably zero temperature.
Say that again. Just the end of the sentence, I didn't understand. Sorry.
So on the next slide,
yeah,
you showed some comparison of your experimental data with some DMRG.
Yes.
Is the data zero temperature?
The data is at zero temperature. Yes.
Right. Okay. So my question would be, so you were kind of mentioning that you were not actually at zero temperature, but at some other state.
Well, the only thing, by showing this graph, the only thing I'm saying is that at zero temperature, you are supposed to have long range order. We know we are not at zero temperature, but still we are kind of have the long range order. So the influence of not being at zero temperature doesn't seem to be a problem. I'm not saying more than that at this level.
Do you have a similar understanding?
No, because it's super difficult to calculate for the antiferromagnetic case. That's the problem, is that for 10 by 10, no one today can provide you a simulation. And that's a big issue, actually, because...
Well, you...
Yeah, we provided it, but there is a debate. Lode Pole at LMU has redone some of the calculation that was done by the guys in Berkeley, and he has actually a slightly different interpretation on the plateau. So he doesn't deny the fact that there is a plateau, but he doesn't claim that this is the kind of long-range order you should have in the ground state. He said it's some kind of metastable state that you prepare and that exhibit long-range order. And the problem is that it's very difficult to actually back that up really by simulation. So in itself, I find it very interesting. I was not expecting this, but this is something which comes from the fact that we have a dynamical process to prepare the state. And in the dynamic, something bizarre occurs. In a sense, for those of you who have followed a bit the spin liquid of Misha Lukin, this is a bit the same story, which is that you have a state which kind of exhibits the properties you want to see, but in the ground state, you were not supposed to have this kind of property. So for us, with the level of disorder we have, what Lode calculates on the initial state preparation fidelity is that you should not have in the thermodynamic limit the long-range order. But the long-range order is on the experiment. We've done many other experiments, and we always see this long-range order. So what is it really? We don't know. And the problem is that at the moment, it's very difficult to kind of do any dynamics on this large size system to kind of decide what this thing is. Which is good. This is exactly what you want. No? There is a bit of a debate, so sure.
So you see the long range order, but of course it's not long range. It's only
only
as long as your experiment, which
sure.
isn't all that long. And so I'm not sure I really understood. It seemed at some point you were implying that that's all it is. It's not really long range order. It's just that it's a finite size system.
I agree.
You expect to see something, some intermediate range order.
But yeah.
Is that enough to explain it? Because it's not.
Okay.
Why don't we let Antoine answer this on the walk over to lunch?